I am Dilan Jayamana. My IIT ID is 2019-284. This is the video demonstration of my final year project. And my final year project's title is Supervised JavaScript Code-to-Code Translator with Relative Positional Encoding Attention Mechanism. So, first I'll start with the problem background. Right? So, code migration is the process of converting source code written in one programming language to another programming language. You have the code base, which is written in one programming language, as an example in Java, and then if you want to convert that into a new, modern, based on the requirement of the company, uh, you may have to convert that into a target language, right? Like this, Java to JavaScript. On translating one code base to another of written in one programming language to another, there are several disadvantages which come up when the developers are doing this task in manual way, right? One is time consumption is high. Developers may have to spend hours to convert large code base manually. Uh, and this is error prone. Developers may accidentally introduce bugs or syntax errors while converting code, and this is costly. So this is an example which I extracted from a research paper. So according to the research paper, there was an incident where the Commonwealth Bank of Australia upgraded its core banking system written in COBOL, which is a very old programming language, which cost more than 1 billion Australian dollars to complete it. So this means that this manual code translation process is much of a costly, error-prone, time-consuming task, right? So, and this requires expertise in both the languages, both in this case in both the Java and JavaScript. When you are manually translating, you may have to face some code quality issues also. As a solution for this, uh, automating code translation is introduced, right? So in automating code translation, these disadvantages will be solved. Practically, most of the developers are experts in few programming languages, but not in every programming languages. So in that case, the gap there will be filled by automating the code translation process, right? Following are the approaches taken to automate code translation tasks. One is rule-based statistical techniques, then phrase-based statistical techniques, then training neural machine translation models, and training large language models. So the usage of large language models have been used lately in the uh, field of research under automating code-to-code translation and several other code translation. Code-related tasks such as NL to code, then code generation, uh, etc. So under training large language models, we are not actually training the models from scratch, but what we are doing is we are gaining the pre-trained weights of the large language models and training on top of that and fine-tuning for our data set, right? So these are some of the supervised models: CodeBird, CodeT5, PLBART, GraphCodeBird, MustCost, and CodeGPT. And these are some of the unsupervised models called Transcoder and TCDOBF. And these are the gaps or limitations identified while I'm doing the literature survey in code-to-code translation task. Um, There is a limitation of existing models pre-trained only for two pairs of programming languages, mostly on Java, C Sharp, and Java Python, or sometimes Java C++. And the existing works show fewer accuracy scores on specific to Java to JavaScript translation. So that was a specific reason why I chose Java to JavaScript or Java JavaScript programming language pairs to do the translation task of, for my final year project. So some existing works are limited to API or snippets, and the limitation of parallel corpus of dataset for most of the programming languages is high. Then extracting the positional information of the code tokens in predictions. The last point is where my contribution comes into place by using a new attention mechanism called relative positional attention mechanism. Now I will go through my contribution or the proposed solution and the limitations that I have addressed. So here I have used a new dataset of Java JavaScript samples originally introduced by Excel Cost. This have been utilized to train graph code but with relative attention mechanism added, which is not trained for Java JavaScript translation tasks beforehand. So the usage of relative positional attention mechanism to graph code BERT, the sec-to-sec model architecture is optimized for the code translation task. This supports extracting positional information of code tokens, uh, encoding the relationships between different code blocks in a complex nested structure of a code. And finally, it supports both program level and snippet level translations. That is because the dataset that I used is a combined dataset of programs and snippets. Okay, now I will explain my uh, project using this concept map that I created. So this code translation task have several branches called limitations, existing techniques that they have used, scope, evaluation, code extraction, attention mechanisms used, application, and dataset. So in this research, the limitations addressed here are highlighted in cream color. So the limitation of not translating, not training for Java to JavaScript translation is addressed, and it uh, the SyntaxSwap supports both snippet and program level translations, and it has a good evaluation score of 79% for only for just 3 epochs. So with the limitation of the resources, I was able to run only 3 epochs using Google Colab Premium GPU. So, and the graph code BERT, the original graph code BERT model was not trained for Java to JavaScript translation task. So those limitations were addressed, and the existing techniques I have used the sec-to-sec architecture and the graph code BERT architecture. Those two models I have been used to do or to perform the translation task in order to train the model. Then scope-wise, this SyntaxSwap code translator tool supports both all the levels here: functions, API mapping, program syntax, and snippets. And the evaluation matrices used in my project, in this SyntaxSwap project, is blow score, exact match score, and the translation edit rate. Originally, the graph code would have implemented these evaluation scores. The logic for the calculation of blow scores and exact match, and I additionally added the translation edit rate evaluation score as well. Then under the code extraction technique, code extraction is one of the most important role in code translation. I mean, in training a model which is able to translate from one programming language to another. So understanding code or semantic information and the data flow of the code is a crucial technique in code translation. Therefore, several techniques have been used in code extraction, like tree-sitter libraries use denoisy autoencoder DOB, code2x, code2sec. Out of them, tree-sitter is proven to be the most feasible way to go with code extraction and the most efficient way. Uh, so this have been originally used by graph codebed because graph codebed highly utilizes the tree-sitter library to create the graph construction, data flow, and understand the code semantics, right? And inherited from that, Excel cost model have been using that also for the translation task. Then attention mechanisms. There are several attention mechanisms that we can involve in this type of a translation model, like sparse attention, multi-head, self-attention, cross-attention. Some of these are already in the models, which are mentioned under supervised or unsupervised. But uh, when I'm going through the researches, I didn't see any usage of relative positional encoding attention mechanism used in an existing research related to code translation. But it have been used for English to German translation. Therefore, I applied this relative position encoding attention mechanism to the graph code bird model architecture, and I modified the graph code bird model architecture. This is a small demonstration on the SyntaxSwap tool I developed behalf of the research project. So here you can basically input the Java code and press on translate and get the JavaScript code. So currently my backend is not running. Let me fire up the backend using Flask run. Now it's available. Let me refresh it. And I'll use the same system.out.println hello world as the input Java code, and I will translate it. So the progress can be seen in the log. So this shows how much of time it took to translate. Uh, and if the translation is successful, I mean, if the translated code does not have any error and it is capable of indenting the code itself by passing through a parser, it will output the translation is successful. So there's a limitation in graph code word. That is because in the data flow extraction or the code extraction part, the string literals are extracted and removed. So what I did was I displayed those string literals which are removed by extracting the string literals from the input code. Right? And this is the abstract syntax tree generated for the target translated code. Now let's translate this. So more the lines, more the complexity of the code that we input, it will take some time to translate. Yeah, translation is successful. So if I accidentally give an erroneous code, input an erroneous code, sometimes the translated code is, sometimes the model is capable of fixing that error and translate the correct code, and sometimes it fails to generate the correct translated, the correct code. At that time, error message is displayed with a red color alert, and an instance of it I have included in my final year dissertation. All right. So first, I will go walk you through the model I used to train. Um, so here, what I am using mainly is the graph code word model, and it is a modified model with an added attention mechanism called relative positional encoding uh, mechanism. So this is the original model architecture. I have included the citations of the code reused here. So in this sector-sec architecture, uh, I have added a class called relative positional encoding. There, what I'm mainly doing is I'm creating a positional table on the code tokens to store the positional information and the structural information of the code tokens, right? So this class is an instance of this class is created as a in the constructor of the sec2sec class, uh, like this. I have updated the uh, code by like this by passing the target embeddings and overriding the target embeddings by the returning embeddings of the relative positional encoding attention mechanism. So then under the predict also I override the target embeddings by passing the target embeddings to the relative positional encoding, and so that is under the forward method, right? So those are the places where I have modified the graph code word model architecture by adding the relative position encoding mechanism, and I have optimized the running code. The training loops and the running code of the model. So here, what I'm doing is I'm mounting the Google Drive and I'm installing the required libraries. Then I'm importing the necessary libraries that I need. This is where the tree sitter library is needed in data flow graph generation. So under the DFG file, you can see this is a code which I have reused. So I have included the citation here. This code is used to generate the data flow graph from a specific programming from a specific code snippet in a specific programming language. So there is a data flow graph for uh, the language which is used here. So my input language is Java. So the data flow graph is generated is for the Java programming language, and this is the code for the Blue evaluation metric calculation. Right, I'll go to the running application again. So this is the function to extract the data flow, and then I created a data set. Sorry, a text data set to pass the data set and prepare the data to train. So for training purpose, I created several versions of my dataset. The dataset is contains of 77,811, which is a high number. I reduced it to smaller data sets to do the experiments, and this is the training loop. So while its training, the evaluations are also calculated. And after the training, I save the model. So then I'm plotting a graph based on the training data. Then sorry Based on the training loss and evaluation loss and the below score achieved, to understand how well the model performs. Then what I do is I load the model and the tokenizer which I have saved before, and I do the testing for unseen data. Right? So there I separately calculate the translation edit rate which I added. So this is the model which I use to train. And going forward, I'll go through the backend application are defined. So here from the front end, it takes a text based on the key Java code. And as I have mentioned earlier, the string literals are extracted. This code snippet will translate the Java code to JavaScript. So the translation logic is here. So it's same as the prediction code which I showed in the earlier code. Um, and this is the front end application, the code for the front end UI. I use React with white, and I use several third-party packages to have the code editor displayed. Finally, I created a small Google form to get some evaluations on the proposed solution on the developed project. For that, I created a small document. So this is the document that I created, and the document which I sent for the evaluators, stating the problem, the limitations, the solution, and the proposed solution that I'm addressing, and several testing results of the model. Talking about the future enhancements, uh, most of the evaluators have suggested to support multi-language support, but I believe by specializing or optimizing this Java to JavaScript translation, uh, uh, pushing it to support more complex translations and add framework level translation support, it will be helpful uh, in the long run. I mean, for the developers. And then I can think of adding multi-language support uh, by adding after adding the full support for a specific two pairs of programming languages, in this case which is Java to JavaScript.